last lecture, we talked about electric forces. And we also talked about static electricity. And we said, if you take something that has a negative charge and you bring it near something that has an evenly distributed charge, that there's this imaginary force field that we don't even have to touch. And all of these negatives will be pushed to the outside because there's some kind of force field around pushing those negatives and attracting the positives. So we can induce this positive charge on one side and negative charge on the other. But you don't even have to touch. And that's because charged particles have force fields around them. And this force field is called the electric field. So if you look at a positive charge, we can illustrate that imaginary force field with these lines called the electric field. And we're always going to imagine that there's this positive test charge, Q naught is defined as a positive test charge. And the reason it's positive is because when we first thought about these things, we didn't know anything about electrons. We either thought we had electricity or not. It's either there or not. We didn't know there was positive protons and negative electrons. Didn't know that. So by definition, the electrons point in the direction of the force on that positive test charge. So if we put the test charge right here, Q naught, it would be pushed away, right? So that is the direction of the field lines, always pushing away from a positive charge. And if we put that test charge here, it would feel attracted to the negative. So the field lines always point towards the negative charge. The units of the field are newtons per coulomb because whether or not something is there, whether or not there's a Q naught there, a charge there, that field still exists in space. It's this imaginary force field, but it only exerts forces on other charges. And it exerts a force of newtons, certain number of newtons per coulomb. The closer you are to the charge, the stronger the field is. And that is represented by the fact that the field lines are closer together when they are in a stronger field. So the closer the field lines are, like right here, versus out here, right? This field is very weak out here. And electric field is a vector. So E, don't confuse Fe with E. Fe is the force of attraction or repulsion between the two charges. And E is, at that location, how much force each coulomb of charge would feel if it was sitting there. So if the field is 200 newtons per coulomb, that means that at that location, a coulomb of charge will feel 200 newtons of force being exerted on it. And it's always going to be there, whether or not the charge is there. Okay. So let's put 2 protons in here. Remember that the charge on a proton is 1.6 e to the negative 12, e to the negative 19 coulombs. And these are going to be separated by 2 micrometers. Okay, so R is going to be 2e to the negative 6 meters. So if we want to find that force between these two, just the force, not the electric field, okay, just the force of repulsion between them, Fe is going to be equal to 8.99 e to the 9 newtons meters squared all over coulomb squared times 1.6 e to the negative 19 coulombs times 1.6 e to the negative 19 coulombs divided by 2e to the negative 6 meters squared. So I'm going to put 8.99 exponent 9 times 0.6 exponent negative 19 times 1.6 exponent negative 19 equals, divided by the quantity, 2 exponent negative 6 squared into quantity equals, and we'll put that in, it's going to be 5.75 e to the negative 17 newtons. So now, if I take that one of the protons away, so let's say I just take away the right proton, at that location of 2 micrometers, right, at this location, any positive charge is going to feel this many newtons. So a way of being able to measure how many newtons any amount of charge would be to find this thing called electric field. An electric field is simply the ratio of whatever the electric force is at that location to the charge at that location. Okay? So the charge that was at that location was the charge of a proton. So if we wanted to figure out what that electric field was, it would be 5.75 e to the negative 17 newtons divided by the charge of that proton, 1.6 e to the negative 19 coulombs. So if I do the math on this, okay, we're just going to leave this here because it's there, divided by 1.6 exponent negative 19 equals 3.59 or 3.60 e to the 2, 3.60 e to the 2, or 360 newtons per coulomb. So a coulomb of charge at this location would feel 360 newtons. If I only had half of a coulomb, it would feel 180 newtons, and so forth. So I can say that at this location, that's how strong the electric field is. I can use that information to figure out exactly how much force a particular charge would feel. So instead of putting, a proton there, right? Let's say that Q naught was 2 coulombs, then E equals Fe all over Q naught. Fe equals E times Q naught. So that would be equal to 360 newtons per coulomb times 2 coulombs, which would be 2 times 36, which would be 720 newtons. So that 2 coulomb charge would feel 720 newtons of force at that location. It's going to be there whether the charge is there or not. And the direction of the field is always going to be, so if we have that proton right here, and we put that distance of 2 microcoulombs, and we have that proton, Q of proton right here, and we say that it is pointing away because this is a positive charge that's producing the field, and the direction of the field is always away from the positive charge. So the electric field is away from the charge, positive, and it has a magnitude of 360 newtons per coulomb. So if this would be different, right? If it was a proton and electron, right? If we put an electron here, how would it be different? Well, the field would still be pushing away, but the electron would feel a force in the opposite direction. So the field is always going to have the direction of the charge that's producing it, not the charge that's at that location. So our base equation is E equals the electric force divided by the charge at that location. And if we put this into the formula, right, this formula is really K, big Q, Q at that location divided by R squared. So you notice that the Q's go away, the little Q's go away, and you're left with this. So if I know that I have a 4 microcoulomb charge, I don't need to know what the charge is near it to find the electric field. The electric field is going to be 8.99 e to the 9 newtons meter squared all over coulombs times 4e to negative 6 coulombs divided by 0.05 meters squared. So 8.99 exponent 9 times 4 exponent negative 6 equals, divided by the quantity, 0.05 squared. And that's 1.44 e to the 7. 1.44 e to the 7 newtons per coulomb. So both our meters cancel out, but only one of the coulombs cancel out. And what's the direction of it? Well, this is a positive charge. So it is a positive, which means away from the charge. If it had been a negative number, if it had come out because we put the negative in there, if it had been a negative microcoulombs, then it would be negative, which would be toward the charge. So let's make sure we understand the difference between Fe and E. They're both vectors, but Fe is a force and it's measured in newtons, and it can be repulsive or attractive. So if it's repulsive, it'll be a negative, and if it's attractive, it'll be positive. E is a force per unit charge. It's measured in newtons per coulomb. It's a quantity that describes a location in space. It doesn't have to have anything there for it to exist. And E fields point in the direction of the Fe on a positive charge. So it's going to be away if big Q is positive, and it's going to be toward if big Q is negative. So remember, we're talking about a big Q, and then we've got some location at some distance R, and if we do have a charge there, it would be little q. But it doesn't have to be there, right? It could not even be there. Q is what's producing that electric field.